Williamson ether synthesis of butyl methyl ether. The Williamson ether synthesis is an organic reaction forming an ether from an organohalide and an alcohol. A Williamson ether synthesis consists of two separate reactions. First is the preparation of an alkoxide, and second is the reaction of alkoxide with the alkyl halide.
Hey everybody, Professor Davis here from ChemSurvival.com and the YouTube channel ChemSurvival. And today, by request, I'll be talking to you a little bit about the Williamson ether synthesis. So the Williamson ether synthesis can be thought of as the reaction between an alcohol and an alkyl halide under basic conditions to create an ether. Now, what really goes on here essentially is we take the R groups from the alcohol and the alkyl halide and we join them to a bridging oxygen. So you can think of this as a way of combining the R group from an alcohol with the R group from an alkyl halide. So before we look at the Williamson ether synthesis itself, let's consider the two different reagents individually. Now, alcohols are weak acids, which means that in an adequately basic environment, we can deprotonate them, removing that hydroxyl proton and creating something called an alkoxide. Now, alkoxide ions are pretty good nucleophiles, especially compared to their neutral alcohol counterparts. So when we create an alkoxide ion, we expect it to attack any electrophilic site that it can get to. So naturally, if we have an alkyl halide, which is of relatively low substitution, say a methyl or a primary or maybe even a secondary alkyl halide, those particular reagents are primed to be attacked by a strong nucleophile by SN2 because they are not as obstructed on the back side of the carbon-halogen bond. So when we have a situation where we can deprotonate our alcohol and we have an alkyl halide which is susceptible to nucleophilic attack, we can expect to make a Williamson ether product by SN2. So let's watch that happen now. Of course, the first step in a Williamson ether synthesis is to generate your nucleophile from your neutral alcohol. We don't tend to store alkoxide reagents on the shelf because they don't last very long. They're pretty reactive and they tend to degrade over time. So let's say that we want to start with something like T-butanol to make a T-butoxide nucleophile. Well, we need something that's pretty basic because remember that alcohol is a pretty weak acid, a pK of about 16. So I'm going to use a very common reagent that's used for this purpose, and that is sodium hydride. Now, when sodium hydride reacts, it's as though hydride ion is the base, and that's a really, really basic species. So the reaction between the two generates hydrogen, which itself has a pKa of about 35, so it's very happy to form out of a hydride ion. And what's even better is that hydrogen will effervesce from the system because it's a gas. This makes the reaction completely irreversible because as the hydrogen evolves and effervesces, it becomes unavailable to react. So now I've created sodium T-butoxide. This is going to be my nucleophile for my Williamson ether synthesis. So once I've generated my alkoxide ion, I expect it to attack any electrophile that it can get to. And in my example here, I've shown you methyl chloride as the substrate. Being a methyl alkyl halide, methyl chloride is extremely well suited to an SN2 reaction. There's really nothing obstructing our alkoxide from attacking. So it will. And we'll go through an SN2 reaction, which will generate our T-butyl methyl ether and a halide ion as a byproduct. So this is an effective way of making T-butyl methyl ether. But remember, I said we can think of this as just switching R groups from an alcohol and an alkyl halide into the two R groups of an ether. So there's always two potential mixtures of reagents for any asymmetrical ether. So the question obviously comes up here is, could we make T-butyl methyl ether using methoxide and T-butyl chloride instead? The answer is no, this is not a very good idea. And the reason, of course, is that that electrophilic carbon there, which I've colored for you in this sort of pinkish color, is buried pretty deeply in T-butyl chloride. Right? If I do a space-filling model, you'll see that there's really not a lot of room in there for a nucleophile to reach. That's a very tiny little target for that nucleophile to try to get to. And even a small nucleophile like methoxide simply can't get in there and attack and have a nucleophilic substitution. So what's going to happen instead? Well, as you can probably imagine, when you mix a SN2' nucleophile with an SN1' substrate, you end up with elimination because you've got those conflicting forces. So since our methoxide ion can't really access the backside of T-butyl chloride for a substitution, it's not going to wait around for a carbocation to form. Instead, it's going to act as a base. And in doing so, it's going to find itself an alpha proton to deprotonate and kick off that leaving group by that mechanism. So when it finds itself a good 180-degree dihedral to an alpha proton, it simply attacks that and removes the proton. And of course, the consequence of this reaction is that we don't create the desired ether, but rather we create the elimination product, an alkene. So whenever we are running a Williamson ether or trying to design a Williamson ether, we have to be careful to select the least substituted alkyl halide possible so that we don't promote this side reaction of elimination from taking place.
The chemicals used in the experiments are 5.5 grams of 1-bromobutane, 8 grams of anhydrous calcium chloride, 3 grams of 25% aqueous calcium chloride, 40 ml of methanol, 1.4 grams disodium methyl.
Experimentation. Step 1. Preparation of sodium methoxide.
Place 40 ml of methanol in a 50 ml round bottom flask and feed the flask with a reflux condenser. Add 1.4 grams of disodium methyl through the top of condenser, allowing the reaction to subside before adding the next piece. If the sodium sticks to the inside of the condenser tube, push it into the reaction flask with a long glass tube or rod.
After the sodium has completely reacted, fit the flask for a simple distillation. Put a stir bar into the reaction flask and distill 25 ml of methanol into a graduated cylinder. If it is necessary to stop the experiment at this point, store the sodium methoxide in the round bottom flask with a heavily greased glass topper.
Step 2. Reaction of sodium methoxide and 1-bromobutane.
Fit the 50 ml round bottom flask containing the sodium methoxide with a reflux condenser.
Cool the flask to room temperature with an ice bath. Weigh 5.5 grams of 1-bromobutane into a flask. Using a dropper, add the 1-bromobutane into the reaction vessel through the top of the condenser in 1 to 2 ml aliquots over about a 2-minute period. Although warming may be required to start the reaction is quite exothermic.
Do not add all the 1-bromobutane in one portion. Cool the reaction flask with an ice bath during the addition. Cork the Erlenmeyer flask between additions so that the 1-bromobutane does not evaporate.
After the addition has been completed, let the reaction vessel stand at room temperature until the exothermic reaction has subsided and the methanol ceases to reflux. Then, heat the mixture at a gentle reflux or simmer for 1/2 hour with a heat plant.
The mixture will bump because of the precipitated solid. Therefore, do not attempt a vigorous reflux.
After the reflux, cool the reaction vessel with a water or ice bath and add 4 to 6 ml of water to the mixture through the reflux condenser. If all the sodium bromide does not dissolve, add a few additional milliliters of water. Dissolving the sodium bromide prevents bumping in the next step.
Equip the flask for simple distillation. Distill the 2-layered mixture, collecting the material that boils up to 64 degrees Celsius. The volume of distillate should be about 8 ml.
Transfer the distillate to a 25 ml separatory funnel and extract it with 3 ml portions of 25% aqueous calcium chloride. The calcium chloride solution is the lower layer in this extraction and the interface is difficult to see.
Pour the product from the separatory funnel into a 25 ml round bottom flask. Add a gram of anhydrous calcium chloride, stopper the flask, and let it stand overnight.
Thank you for watching.